So let's take a look at the next section. This is on angular and linear velocities. Did I hear moaning? Is that what I heard? Did I hear moaning when I said that? Okay. All right. So if we're talking about a velocity, usually we're measuring a distance or something like that per unit of time. So you would recognize these as velocities. So like feet per second, miles per hour, meters per second, kilometers per minute. Any of those is a velocity. Okay? In every single one of those, we've got a distance on the top and a unit of time on the bottom. All right? So those are all very familiar. They come from the formula that connects distance, rate, and time. And what is that formula? Okay, so distance equals rate times time. And we can take that and we can tweak it however we want. If we want to solve for time or we want to solve for the rate, we can do that. Now, angular velocity is one of the things that we're going to study in this section, and it's quite a bit less familiar to us than those like miles per hour. Everybody knows that. Okay, everybody's really familiar with that. So, the name kind of says it all. Angular velocity measures the angle an object turns per unit of time. It's not a distance, it's an angle or an amount that it turns per unit of time. So, the units on the top need to be an angle measurement, and the units on the bottom, it's still going to be a velocity, need to be a time measurement. Now, one type of angular velocity that you're probably familiar with, you probably at least heard it, is RPM. So what does RPM stand for? Okay, so those are revolutions per minute. Revolutions per minute. Okay, now, depending on the textbook or the author or the mathematician you're talking to, some people would say revolutions per minute that truly is an angular velocity, and some people would say, well, it's not quite because it's not an angle. It's not a measurement for an angle. Okay, but if I said I'm going to go all the way around, that is kind of an angle. Okay, we usually like to work with things that are more precise. Okay, so we're going to take 400 revolutions per minute, and we're going to turn that into an angular velocity. We want an angle measurement on the top and a unit of time on the bottom. So we're going to write it like this. This is 400. Now I'm not going to write the word RPM because RPM isn't very mathematical. I'm going to write this, revolutions per minute. And then I'm going to ask a question. If this is a fraction, is 400 a fraction? Yeah, it is. We can just put it over 1. So here's really what we mean. This means 400 revolutions every 1 minute. Okay, so that sounds a little bit weird. 400 RPMs is a lot easier to say. We're talking about 400 revolutions every 1 minute. Okay, so every time a minute goes by, there go another 400 revolutions. Well, what we'd like to do is we'd like to make this an angle. So we'd like to turn revolutions into an angle. And this is where we go back to what we talked about last week. Conversion factors. Does anybody remember what a conversion factor is? Or what my definition of a conversion factor was? It's a funny looking one. Okay, so what we want to do is we want to cancel off that revolution. So let's think about this for just a second. One revolution in terms of angles would be what? Okay, I could either do 360 degrees or I could say one revolution is 2 pi radians, right? Now, after our discussion last week, which one am I going to like better? Am I going to like the 360 degrees or the 2 pi? Probably 2 pi. Can anybody remind us what advantage radian measure has? Yes, Randy. You don't have to convert it. It kind of already tells you what fraction of the circle we're working with. So it works really well in equations or in formulas. Okay, and we're going to have a bunch of formulas today. So we want to use radian measure. So here's what we do. Since these two things are equivalent, let's make a conversion factor out of them. We're going to times by. Now, if I want the revolutions to go away, where do I put the revolutions? Top or bottom? Put it on the bottom. So I'm going to put one revolution on the bottom, and I'm going to put 2 pi radians on the top. I can then cancel revolution here with revolution there. This is going to give me, let's see, 400 times 2 pi. I'm going to leave this in exact form. This is going to be 800 pi and this is radians per minute. Again, angular velocities are much less familiar to us. They sound a little bit weird, but this is 800 pi radians per minute. How many radiuses we turn every minute. Okay? Now, because these are used a lot, we usually use a symbol to represent angular velocities. If any of you are going to go into physics or engineering or anything, get used to seeing Greek letters a lot. So we're going to use this Greek letter right here. This is the Greek letter omega. Okay, it looks kind of like a funny looking W. And here's how we write down omega. Omega is the angle, and remember we were using the Greek letter alpha for an angle last week. It's the angle divided by the time. So does this match up with what we had here? Is this an angle on the top? Is 800 pi radians, is that an angle? Yep. And a unit of time on the bottom? You bet. Okay? So that qualifies. Okay. So now we're going to do some problems, and we're going to see this one over and over again. By the way, we're 3 days into class. If I slide this up too quickly or you need something expanded or blown up, just let me know and I'll highlight that for you. Okay? Everybody good to move on? We're good on speed? Nice pace? Okay. Let's take a look at example number 2. We're going to start with this example and then we're going to tweak it several times. It says we've got a 22-inch lawnmower blade. It rotates at 2,500 RPMs. What is omega in radians per minute for a point at the tip of the blade? Okay. So we've got this. So pretend I don't advise this at home, but let's say we tilted our lawnmower on its side. Here's the blade. We're taking a look at that. It's 22 inches in diameter, and it's spinning at 2,500 RPM. Question here is, what is omega? Or in other words, what is the angular velocity? Okay. How many degrees or how many radians does the tip of the blade turn per unit of time? So this right here is the key to figuring this out. We already did a problem with RPMs. RPMs is nearly an acceptable angular velocity. We're going to take this and we're going to say, all right, we had 2,500, and we'll write it this way again, revolutions per minute. I want to change that into radians per minute. So I do that same conversion factor. I'm going to take 1 revolution. That's the same as 2 pi radians. So on this problem, that means that omega is, let's see, that's going to be 2,500 times 2 times pi. So that's going to be 5,000 pi. Let me make some more space here. 5,000 pi radians per minute. Everybody okay with that? Easy enough? Just like the problem we did before. Next part of the question is, convert your answer in part A to radians per hour. So we had 5,000 pi radians per minute. I want to know how many radians per hour that is. So we'll convert that. What do I want to cancel off? I want to cancel off minutes, so I'm going to put minutes on the top. I want hours on the bottom. So all I have to do is put something there where those two things are equal. So this truly is a funny looking one. 60 minutes is 1 hour. So this is going to be, what do we got there? 30,000 pi radians per hour. That's a lot. Yeah.
Isn't it 300,000?
You're right, 300,000. Yep, thank you. So I have Jerem here. He gets a check after class every day. He finds me make a mistake. It's a small check though, right? Okay. So let's take a look at the next question and think about that for just a second. What is omega in radians per minute for a point that's 4 inches from the center of the blade? Anybody know? It's exactly the same, isn't it? Okay? So it's going to be 5,000 pi radians per minute. Can somebody explain to me why it's the same? Brandy.
Because
It's one solid piece of steel. If I take the point that's 4 inches from the center and the point that's 11 inches from the center, because remember that's the radius, if this one makes 1 revolution, it drags this one with it. Okay? And if this were a gigantic, say we had a 10-foot lawnmower blade, okay? That point that's out at the end is going to make 1 revolution every time one that's 4 inches or 1 inches or 2 feet from the center. Okay? They're all going to go around. They're going to spin, turn through the same angles at exactly the same rate. Does that make sense? It doesn't have anything to do with how big the circle is. Okay? So angular velocity really isn't that bad, is it? It's pretty easy, isn't it? Okay, so let's take a look at the next problem. In example 3, it says this: the Earth makes 1 rotation every day. Well, that's said a little bit differently, but have they kind of given us enough information to figure out what the angular velocity is? You bet. 1 revolution every day. We didn't say RPMs. Okay, it's not revolutions per minute, it would be revolutions per day. So here's what we've got. Omega right now would be 1 revolution every 1 day. Well, we don't want that in revolutions per day. We want that in radians per hour. So we need to change both units here. So we're going to take, let's see, I don't want revolutions anymore, I want radians. So we're going to do the same conversion. 1 revolution is going to be 2 pi radians, 1 full circle, 1 revolution. I can cancel off the revolutions. Now I have radians per day. So I'm almost there, but we wanted radians per hour. So what do I want to cancel off now? I want to cancel off the days. So 1 day is the same as, what unit do I want down here? 24 hours. I can then cancel that day with that day, and if we look through here, the only unit on the top is radians. So this is 2 pi radians. And the only unit on the bottom is 24 hours. So then I can simplify this. I'm going to write this as pi twelfths. Everybody okay with that? Pi twelfths, radians per hour. Okay, any questions? Good. How many degrees is that? 15 degrees. Okay, it would be half of pi 6. Pi twelfths is half of pi 6, so that would be half of 30. That would be 15 degrees. Okay? Does that make sense that it's pi twelfths radians? What if we let 24 hours go by? 24 pi twelfths, that would be 2 pi. That would be 1 full revolution, because 1 revolution is 2 pi. Next question, what is omega for us here in Salt Lake City? How fast are we spinning? Exactly the same. We're on the Earth, right? It doesn't matter where you are on the Earth. Some of us are. David, maybe not so much. Okay? So it's also pi twelfths radians per hour. Okay? All right. So now that we've got angular velocity figured out, let's talk about linear velocity. Okay? Linear velocity is a distance per unit of time. Not an angle per unit of time, but a distance per unit of time. So if we use this formula right here that we're all familiar with, d equals RT, or better yet, if we're going to talk about a rate, the rate we're talking about is kind of like a speed, it's a velocity. So let's talk about distance equals velocity times time. If we solve this for v, well, I just divide both sides by t, I get distance divided by time. So in order to figure out a linear velocity, you need to know how much distance you've covered, divide that by how much time it took you to cover that. So let's go back to this lawnmower problem again. 22-inch lawnmower blade rotates at 2,500 RPM. We already know the angular velocity here. It says, what is the linear velocity in inches per minute for a point at the tip of the blade? So how fast in inches per minute is the tip of the blade going? Okay, we could kind of muscle our way through this. Okay, we could figure it out that way. So we could figure this out. Let's see, if we've got this blade here and it spins around like this, so it starts right there, we could figure out how far it goes in 1 revolution. How would we figure that out? Circumference. Circumference equals 2 pi r. So that would be 22 pi inches. That's one revolution. How many times does it spin around a minute? 2,500 RPMs. So if every time it goes around, it goes 22 pi inches. If you want to throw that in your calculator and get a decimal for that, that's fine with me. But it does that 2,500 times every minute. So we're going to take this, and what are we going to do with it to get the answer? Times by what? Times by 2,500. Okay, everybody watch, please. Does everybody agree that this would give us the right answer? Okay, because it said inches per minute. This is in inches. It does this many in a minute. So we should be okay. We all right with that? Okay, watch. Most people forget this. Here's what we just figured out. It's 22 pi inches in one revolution. It's 2,500 what? Revolutions per minute. And look at this. Revolutions cancels with revolutions. What's the only unit on the top? Only inches. What's the only unit on the bottom? Minutes. Do we have the right answer? Yes, we do.
Would the circumference be 44?
No, the radius is 11. Okay?
Oh.
Its diameter would be 22. Okay? Good question, though. Everybody good there? Sure? Okay, so if we multiply the 22 and the 2,500, correct me if I'm wrong, but that's going to be 5,500 pi inches per minute. 55,000. Okay, thanks. No check for you. Yeah.
I have a question. So, why did you want to find the circumference of it first?
Because if we've got a point, say you're a little bug on the end of the lawnmower blade, and you're going to travel around here 2,500 times every minute, what we want to know is, what's the linear velocity? What distance did we cover, divided by the time that it took us to cover that distance? So one revolution would be one circumference. So that's going to be the 2 pi r, or the 22 pi inches. And we do that 2,500 times every minute, so we just times it by 2,500. Does that make sense? Good there? Okay. Let's convert this to miles per hour. Convert this to miles per hour. So I'm going to take this. So there's the answer to that first part. If we want miles per hour, I need to change the inches to miles, and I need to change the minutes into hours. So let's do the inches first. 12 inches is 1 foot. Inches cancel. Next. I don't want feet. What do I want? I want miles. So I do 5,280 feet is 1 mile. Feet cancel. Okay, what are my units right now? Miles per minute. I want miles per hour. So I want to cancel off the minutes. So I do 60 minutes in 1 hour. Cancel off the minutes and take a good look there. Miles on the top, hours on the bottom. Now, I would advise a calculator at this point, because here's what we've got to do. 55,000 pi times 60 on the top and 12 times 5280 on the bottom. And that's going to be in miles per hour. So let's grab a calculator, type that stuff in. So 55,000, and then I do a pi, and then I do times 60, and then I do divide. Everybody watch, please. 12 times 5280. Now, take a look. Is that going to give me the right answer? Why not? Okay. It's going to divide by 12, and then it's going to times by 5280. I need a set of parentheses here. I need the entire top divided by the bottom, so I'm going to insert a set of parentheses there. Because it's all multiplication on the top, I can get away with just putting the bottom in parentheses. Okay, put that right there. What does that mean? 163.2 miles per hour. So if you're that bug on the end of the lawnmower blade, you're going 163 miles per hour. I would actually imagine, I don't know, but I would imagine that's probably pretty accurate. Okay, lawnmower blades probably do spin about 2,500 RPM. Not sure, but it's probably somewhere in that neighborhood. Okay, so the tip of the blade is going 163 miles per hour. Any questions? Okay, let's see. Flip the page over. So that problem there was just done kind of using brute force. We kind of just went through and said, okay, how would I figure this out? We're just thinking our way through it. There's a much more effective way. We can kind of develop a formula to figure out linear velocities for us. And here's kind of the rationale. So you'll remember arc length. Gosh, because we already went over that. What was the arc length formula? There you go, alpha times r. Okay? So remember, arc length is just the distance around the outside of the circle, how much you go. So that would be an arc length right there if we went maybe a fourth of the circle. It's just the distance, the linear distance around the outside of the circle. Okay? Since the velocity, like we showed earlier, would be the distance divided by the time, we could replace the distance with this formula that tells us the distance around the outside of a circle. Replace it with the arc length. Okay? So this would be S over T, arc length over T, because this is a distance. It's a distance around the outside of the circle. So let's take a good look at this right here. If this is what arc length is, we can write it like this. Just replace the S with an alpha R. Let's break this up just a little bit. Could we rewrite this somehow using the properties of fractions? Let's write it as two separate fractions, yeah.
S over T is equal to AR over T.
Yep, AR over T is what we've got right here. Could we break this one up? Okay, you could do A times R over T, but we want to split it into two pieces. How about this? Alpha over T times R. Isn't that the same thing? If I wanted to, I could put a 1 on the bottom of that. I have A times R on the top, and I have T times 1 on the bottom. Isn't that still the same thing? Okay, this is just fine. We have the angle that we turn to through divided by T times the radius of the circle. Or does this look familiar right here? What is alpha over T? Javier's flipping on the back side of the paper. What is it? It's omega. So linear velocity can be found from angular velocity. All we do is we take the angular velocity, angular velocity, and multiply it by, what does R stand for? Radius. Okay? And that will give you, this right here is the linear velocity. Okay? So, the two formulas that you need to have so far are this one right here. This one would be good to have, not absolutely necessary. It's kind of a good stepping stone. Okay? And this guy right here on the first page. Okay? You need to know those. Those are going to get used a lot. And the cool thing is, if you know those and you know some algebra and are really good at algebra, we can do some pretty complicated problems. So let's take a look at example 4. This is going to look familiar. 22-inch lawnmower blade rotates at 2,500 RPM. What is the linear velocity in miles per hour for a point at the tip of the blade? Hint is use the formula above and then convert the units. Okay, we want linear velocity. We want to know the velocity. What's the angular velocity for this lawnmower blade? What was omega? We figured it out on the back side. What was it? 5,000. 5,000 pi radians per minute, right? Okay, this right here is our omega. Let me change colors here. That right there is omega. We're going to times it by, we need to times it by the radius. Now, look at that problem. What is the radius? 11. Okay? 22 inches all the way across. This is going to be times 11 inches. Now, the book glosses over this fact. I'd like you to pay attention. If you do these correctly, the units work out perfectly. 11 inches is equivalent to what on this problem? 1 radius or 1 radian. Use them interchangeably. So this is exactly the same as 1 radius. So the book does this. It kind of waves its hands and say, hey, you know what, this works out in inches per minute, and we're all set to go. The reason this unit goes away, the reason that radius, radian, and that radius go away, is because they're the same thing. That's why they cancel. I now have this in inches per minute. What did they want the answer in? Miles per hour. So then we'd go through the other conversions. Let's just take a quick look. We want this in miles, 12 inches, 1 foot, 5,280 feet in 1 mile. I'm in good shape here as far as the units go. The inches have canceled and the feet have canceled. And then the only other thing I need to do is get rid of the minutes. And I'm going to do 60 minutes, so that will cancel off with the minute on the bottom, and that's 1 hour. Now, correct me if I'm wrong. Let's not belabor the point, but aren't these the exact same calculations that we did on the bottom of the front page? So isn't the answer going to work out to be the same, 163.2 miles per hour? Okay, we just got it a different way, didn't we? Okay? Now, here's where it starts, yeah.
Where did you get the 11 inches from?
Because that's the radius. If it's 22 all the way across, it's going to be 11 inches for a radius. Good? Everybody got that? Okay, now it's going to get a little bit interesting. What is the linear velocity? So that's the linear velocity for a bug on the end of the lawnmower blade. What if that bug moves so it's only 4 inches from the center of the blade? Now before we asked about angular velocity. Bug out here and bug right here, they spin around. They both spin around at the same rate. But what if we talk about the distance that they cover? One's going faster. Which one's going faster? The one closer. So let's compute this. We want the velocity for this bug that's only 4 inches from the center. We already agreed omega is going to be the same, so this is going to be 5,000 pi radians per minute. How far is it from the center? What's its radius? 4 inches. Okay, in 1 radius. Those are going to cancel. I'm going to run through. You don't have to do all of this if you just want to watch. Okay, I'm going to go through and do the same conversions because I still have inches per minute. I'm going to do 1 foot, 12 inches. I'm going to do 1 mile, 5,280 feet. And the final conversion is to change it into the correct unit of time, 1 hour. I'm going to recall this on my calculator. There it is right there. Let's see. So there's the conversion I need to do. This was only 25, let's see, it's 5,000 times 4, right? Insert a 4. You okay with that? What does this mean? The bug's going slower. So we're about 59.49 miles per hour. Why is it going slower?
Because it's the business area.
Because he's only 4 inches from the center. He doesn't have to travel as far every time he goes around. The further you go out, the bigger your circle is, even for the same angular velocity, even if you're spinning at the same rate, your linear velocity, how fast you're physically moving, okay, in a distance per unit of time, is going to be less because your radius is smaller. Does that make sense? Okay, then let's look at some practical applications of this. Okay, the Earth has a circumference of approximately 24,818.58 miles. That means the radius of the Earth at the equator is about 3,950 miles. So if we look at the Earth from above, the distance around here is about 25,000. The radius is 3,950. Okay? So if you went from the center of the Earth out to the equator, you're going to travel almost 4,000 miles. Okay? Find the angular velocity for a person standing at the equator. They're on the Earth, just like we're in Salt Lake City on the Earth. What is our angular velocity? 15 degrees per hour, or pi 12ths radians per hour. There's the answer for that one. Already got that one. Find the linear velocity for a person standing on the Earth's equator in miles per hour. So, linear velocity is where we apply that formula. We have to know how fast it's spinning, what's its angular velocity, multiplied by the radius. Here's what we're going to get. The linear velocity would be pi 12ths radians per hour. And then what radius do we multiply by? If you're at the equator, how far are you from the axis of the Earth? 3950. So 3950 miles in one radius. Those cancel. So the only unit that I have is miles on the top, 3950 pi divided by 12, and that's going to be miles per hour. Let's throw that in the calculator. Somebody go ahead and throw that in. 3950 times pi divided by 12. Say 1024. I'm just guessing. What is it? What is it? 1034? Point what? 0.1. Okay? So if you're at the equator and you're just standing there, how fast are you really going? 1,034 miles per hour. Okay? Now, let's look at the Earth from the side. So here's the equator. If you're right here on the equator, you're going over 1,000 miles per hour. If you're up here where Salt Lake City is, we're about 40 degrees north latitude, so we're about right here. And the Earth's axis is right here. So if this is 3950, this is a little bit less. Okay? It's actually about 3,000 miles. So if a bug at the equator is going 1,000 miles per hour, how fast is a bug in Salt Lake City going to be going? Faster or slower? Slower. Why?
Because it's
Shorter radius, we're closest to the axis of rotation. Okay, is the way we'd say that. So our velocity here in Salt Lake City is going to be 12 pi radians per hour times 3,000 miles per hour. And somebody's going to be kind enough to throw that in their calculator. So what's 3,000 pi divided by 12? Jerem, what am I paying you for? Come on.
50 pi.
What is it? 785.4 miles per hour. So we're still going pretty darn fast. Now, so we've got a person at the equator. We've got a person in Salt Lake City. What if we have a person who's only 1 mile from the North Pole?
He's getting ahead.
Probably. Well, is he spinning very fast? No faster than us. Is he moving very fast? Let's do the calculation. Pi 12ths radians per hour times, what's his radius? 1 mile. Whoops, 1 mile is his radius. Those will cancel. So this is pi divided by 12. That's in miles per hour. Let's see, I can do that. 3.14 divided by 12. That's going to be a little bit less than a quarter, right? What is it? Point what? 0.26? Okay, 0.26, a little more than a quarter. Miles per hour. So we go from 1,000 miles per hour at the equator, 700 something miles per hour in Salt Lake City. If you're about a mile from the North Pole, your linear velocity is only about a quarter of a mile in an hour. That's like from here to the entrance. That's all you move in an hour. Versus 1,000 miles, halfway across the United States practically. Okay? All right. And then it says, find the angular and linear velocity for a person standing at the North Pole. So what if you're right on the North Pole? Are you on the Earth? Okay, so what's omega? Pi 12ths. You're standing there, right? Here's what would happen. Every 24 hours, you do one of these. That's it. So about every hour, you get to do this. That's about it. Okay? What's your linear velocity at the North Pole? What's omega? No, omega is pi 12ths. You're still spinning, right? What's your radius if you're right at the North Pole? 0. Okay? Did you see that? Did you notice? I did this. Did I go anywhere though? Did I cover any distance? Nope, I just turned around in a big circle. So, thought questions to finish up. Why does the U.S. launch spacecraft in Florida?
Because it's closer to the equator.
It's closer to the equator. They're spinning faster. Does anybody know? It's called escape velocity. How fast do they have to be going to escape the gravitational pull of the Earth? Of course you did. Yeah. 17,500 miles an hour. So if you had a choice of launching at the equator or launching at the North Pole, which one gives you a better head start? The equator does. That's why the French, they launched theirs in French Guiana, okay, right near the equator. So they have to take all of that stuff. Doesn't matter where you launch on Earth, but you've still got to get up to 17,500 miles per hour. So if you start at 1,000, that stuff's already moving, okay? You only have to make up the other 16,500. Launch it at the North or South Pole, you've got to do all 17,500 yourself, okay? Please take a good look at number 35 and 38. Read them carefully. I'm going to give you a hint. Think about these formulas right here. It's just an algebra formula. It works the same as any other algebra formula. If you have three variables, if you have three variables and they give you two, can you solve for the other one? Absolutely. Okay? Have a great day. Okay. You've been gone. I'm going to be done. If you have the syllabus acknowledgement signature form, bring that up, please.
I have a question real fast. So, when you're saying that, like with the lawnmower blade, that 11 inches equals 1 radius. So,
Yeah, 11 inches equals 1 radius
So that's just
and 1 radius. Okay? So if you did this, let me save this real quick. So if I have a circle and the radius is 11 inches, okay, if I took that and I did 11 inches here, 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 11 inches here. Okay, if I did 6 of them, I'd be just short of all the way around the circle. If I did 0.28 of a radius, okay, whatever that is, however many inches that, maybe 3 inches, that would put me all the way around. So that's why it's 6 pi radians or radiuses.
I saw you there. I need to get onto your roll.
Okay. You're probably on there. Let's see. Elizabeth Martinez. Is that how you say it, Elizabeth?
Yeah, that's how it's legally so.
Oh, it's supposed to be Elizabeth?
That's how my parents wrote it.
And it's Martinez Sanchez?
Yes.
I was like, that looks like pretty much.
Did they spell that right with an S?
No, you're gonna be.
Do you need my
Oh, yeah.
I know.
There you go.
I keep the paper.
What? Oh, did you?
Yeah, I don't remember the box. They use the same exact.
Oh, no kidding.
I forgot to get the 1.3.
Let me go grab it.
Oh, yeah.